Hello there. We have video number 28. This is chapter 11, section 5. Yeah. And this is all about the binomial theorem. And Pascal's triangle. I will do a better job of trying not to jam stuff into your notes like I jammed stuff into mine. My notebook has very few pages in it. I'm trying to get the rest of the year to fit in it. All right, so this is all about expanding out binomials expanding binomials in the form x plus y to the n. And the n could be, you're going to see some that are like 100. I know, it's crazy. So, typically if you saw like x minus 3, don't write this down. If you saw x minus 3 to the fourth, that'd be x minus 3 times x minus 3 times x minus 3 times x minus 3. And you could like foil these, and you'd get x squared minus 6x plus 9. And then another one. See why I'm not having you write this down? And then you'd have to like super foil this, and you'd get like something with like a lot of terms. What this does, this binomial theorem gives you basically a formula to generate all of this without doing all of this. So you don't have to do all the foiling. You can just generate all the terms. And then Pascal's triangle gives you kind of even a shortcut to that. So we're going to do the binomial theorem first, and then we're going to do Pascal's triangle. And the reason we're going to do both is because there are some questions that are like, give me the 8th term in the binomial expansion of blah. Well, Pascal's triangle is only useful if you want the entire expansion. If you want all of just one term, you need to know the formula for the binomial theorem. So we're going to talk about how to do that first. So I'm going to get rid of this because we don't need this. All right, so we're going to expand some of these things. Here is what you do need to write down. And this is already done for you, but if you want to actually be crazy and do this multiplication, feel free. So here's some x plus y to the 0. And anything to the 0 is 1, right? So even though there's variables in there, that's actually 1. And then x plus y to the first power is just x plus y. And then x plus y. So what I'm doing here is I'm increasing the n as we go. And then what's going to happen here is we're going to get x squared plus 2xy plus y squared. We're going to do this down to the 5th, where n is 5. So then we have x plus y to the 3rd. And this is x cubed plus 3x squared y plus 3xy squared plus y cubed. And then we have x plus y to the 4th. And this is x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. And then x plus y to the 5th. And that's x to the 5th plus 5 x to the 4th y plus 10, excuse me, x to the 3rd y to the 2nd plus another 10 x to the 2nd y to the 3rd plus 5 x, y to the fourth plus y to the fifth. All right, so there's some observations here that it's important that you make, and I need to be able to point these out to you. So, one, the first term always has in this case, because there's coefficients here, are just 1 on the x and 1 on the y. So the power on the first term matches the n. Okay, you should notice that. Also, the power on the last term matches the n, but it's the second variable, right? And then take a look at, in this last one, x plus y to the fifth. Look at what happens. I'm going to underline the powers on the x's. You have x to the fifth, x to the fourth, x to the third, x to the second, x to the first, and then you have no x at all. So this is really like x to the 0, which becomes 1, right? And then in light blue, no, we'll do pink because that'll show up. Let's look at the y's. We have y to the 0, y to the 1, y to the second, y to the third, y to the fourth, y to the fifth. That's actually happening in every single one of these. It's just not as obvious with some. Like, let's look at the fourth. So let's look at the y's in this x plus y to the fourth. So I'm looking at this line. Okay, so we have y to the 0, which is 1, which means it's gone. Y to the first, y to the second, y to the third, y to the fourth. So it goes from 0 on the left, and it builds in every single term until you get to n, right? That's n. Okay, this is a 1 here, which is n. All right, so, and then if you look at I did the x's in green. The x's start at n and decrease by 1. So they go 4, 3, 2, 1, and then none. And that happens every time. 3, 2, 1, none. Every single time. The coefficients, numbers in front of the variables, have this, like, notice it's 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. So there's this kind of a pattern happening here, right? So we're going to actually write down 4 observations from that information. Okay, so observations from the binomial expansions. 1. In each expansion, and we didn't even talk about this, there are n plus 1 terms. Okay, so let's talk about that. In this one, n is 0. There's 1 term. Well, 0 plus 1 is 1. In this one, n is 1. There are 2 terms. In this one, n is 2. There are 3 terms, and so on and so forth. Okay, next. 2. In each expression, I gotta move that up. Maybe that says expansion. It does. I read that wrong. In each expansion, x and y have symmetric roles. The powers on x decrease by 1. I mean, you could get even more specific and say begin with n and decrease by 1 as the powers on y increase by 1. And again, you could say begin at 0 and increase by 1. Okay. Number 3. Let's see, what color do I want here next? Number 3, the sum of the powers in each term equals n. So let's go take a look at that. In the fifth one, for example, we have the first term, 5 plus 0 is 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 1 plus 4 is 5, and 0 plus 5 is 5. So that needs to happen in every single term. That will happen in every single term. And lastly, number 4, the coefficients increase and decrease in a symmetric pattern. And these follow both Pascal's triangle and the definition of combinations. Both will be discussed in this chapter. Okay, I feel another long video coming on. All right, the binomial theorem. So in the expansion, I keep doing that, of x plus y raised to the n power, this is equal to x plus y to the n is equal to, oh no, don't need that. I'm worried about we're getting this all in this line. So let's see, x to the n, y to the 0, as we saw above. So this will match the power there, plus n. I don't know, I didn't point that out up here. The first index, or the first coefficient, is always the same as n, right? So that's what this is saying here. Let me go back to my pen. So n times x to the n minus 1, y to the 1, plus dot, dot, dot. And then we're going to have something you've never seen before. C to the n on one side, r on the other. Those are both subscripts. Make sure they're little. X to the n minus r. We'll talk about what that means. Y to the r. It's just something you're going to stick in a calculator. Plus n x y to the n minus 1. So that's an x to the first power there. Plus x to the 0, y to the 1. All right, where the coefficient of x to the n minus r, y to the r is c to the n r, is equal to n factorial over r factorial times n minus r factorial. And we've talked a little bit about factorials, but mostly we're going to use Desmos to do this. It can be done in a graphing calculator. I'm not really sure how to do that. I think we can figure it out though. So if you need help, you could try a YouTube video, or I can probably manage to help you with that. All right, so get all that in your notes, and then some info on, we already did the info on combination or factorials, so I don't need that here. So using this definition right here, let's look at a couple things you need to know about the definition of those factorials. So let's look at this. Let's do, one other thing that you need to know, that NCR is also in the Desmos calculator, it's written like this. Okay, so I will be teaching you how to use that, but if you see me write it like this, you know what the heck is happening. All right, so what we're going to do is we're going to use this formula and actually evaluate this. So this is our n and this is our r. So we're going to go 6 factorial over 0 factorial times 6 minus 0 factorial. Well, 0 factorial is 1, so this cancels out and goes to 1. And then this simplifies to 6 factorial over 6 factorial. 6 factorial over 6 factorial, just like any number over itself, is 1. So there's a generalization that you can make, and that is this. Anytime r is equal to 0, the combination equals 1. No matter what n is, doesn't matter. Okay, so that will be true all the time. Let's take a look at this guy. You need that formula. Okay, so let's look at if that is a 1 down there. Well, that means C6, 1. So we're going to go 6 factorial over r factorial is 1 factorial times 6 minus 1 factorial, which means I have 6 factorial. 1 factorial is just 1. So this is a 5 factorial. So check this out. And this is always going to be, so if this is a 1, this is always going to be 1 less than, the denominator will be 1 less than the numerator. Well, look at what I have here. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And the bottom is 5 times 4 times 3 times 2 times 1. So these all cancel each other out. Oh, that was weird. Did you see that? I'm not even going to fix it. So that means all I have left is 6. Okay, so another generalization. Anytime r is 1, the combination equals n. Okay, and that will always be true because your denominator is always going to be 1 less than the numerator, canceling everything out except that leading number in the numerator. Okay, so that's always going to happen. Now, let's go. I'm going to attach my keyboard really quickly because this works a lot better when I use my keyboard. And then we're going to go to Desmos and take a look at how to use this in Desmos. So I'm going to go to the scientific calculator, and here's what you're going to want. If I wanted to evaluate, I don't know, let's say the combination of, excuse me, 10 comma 3, you're going to go and you can see, normally you're on this main screen. Okay. So we're going to go to this function screen. And at the bottom of the functions, you see this NCR. We're going to click on that. And it puts that into the screen. And you're just going to put the two numbers with the comma in between. So if I do the 6 comma 0, we should expect to get 1. So 6 comma 0. You get a 1 over there on the right hand side. Okay. If I change the 0 to a 1, we should get a 6. Okay. So now let's do a, I don't know, 10 comma 3. 10 comma 3. 120. All right. So if you have any kind of strange things in here, big numbers, you can just come to Desmos and utilize this. And I've got these on my paper, so I'm not going to keep coming back here and coming back and showing you how to do these, but just come to the Desmos Scientific Calculator. Remember, you want to use, you've got your main and your function. Just come to your function, click on your NCR, and then you type in your N is the first number, R is the second, and the answer is over here on the right-hand side, okay? And in this section, that's all we're using. In the next section, we're going to be using these PRs. A C is a combination. A P is a permutation. They both have an N and an R. They mean different things. So they'll be more explained in the next section. Right now, you just need to know how to use the CR, the combinations. Okay? So that's how you can use Desmos to do that for you. I'm going to jump back to this screen, unattach my keyboard, and we'll get back to this lecture. Okay, so here is what we are going to do and how you're going to use this piece of information. Now, keep in mind this bit of info in this pink box right here. Okay, actually, this whole bit of info, let me just highlight this whole bit of info is all kind of super important. All right, I'm going to be utilizing that and writing that down in the next problem. So when I do write that down, just recall that it's coming straight out of the definition of the binomial theorem. Okay? All right, so let's get some paper. And here is the question. Pen, purple. Okay, so find the sixth term in the expansion of 2x plus 3y to the 11th. Okay, and then I made a note that you may want to put in your notes. So from the definition of the binomial theorem, any term can be found by using the formula NCR. So that's going to be our coefficient, x to the n minus r and y to the r. Now you have to be a little bit careful here because I'm going to do a little bit of highlighting. The x is actually this whole thing. So you have a 2x is the x, and we'll make these distinctly different. The y is this entire 3y. So I'll point out how that's going to get thrown in there here when we do this. Okay, so we're going to take and use, let's look at what we know. So n is the number of terms well, n is it's the exponent on the expansion. Let's just put that. That's easier. Just grammatical information. Okay, so we have this piece of information. All right. And I'm having a little bit of a brain fart. I can't remember where the R comes from. We want the sixth term. Oh, okay. I know where that's coming from. Okay, so kind of here's how I did this in my notes. I wrote down, we have a sub 1 would be represented by this. C, the n is the 11, and we're starting at 0. And then a sub 2 would look like c to the 11 with a 1. A sub 3, a sub 4. We want a sub 6, right? I'm going to give you a generality. You can see how well it works. So clearly it needs some highlighting. We have c to the 11, 2. And then this is going to be c to the 11 and 3, c to the 11 and 4. So this is where our coefficients are coming from. Okay, so you're always starting at 0 for the first coefficient because it's going to be a 1. Now, we want the sixth term, right? Now, here's kind of the note that needed some highlighting. Since a sub 1 begins with r equal to 0, meaning this guy right here, in future problems, you can say, you can determine r by saying it's the number of term you want minus 1. Okay, so we wanted the sixth term, so we'd put in 6 minus 1, and r would equal 5, which is what we got here. But if you had if you wanted the 11th term, you don't want to have to sit and draw these all out. Just take 11 minus 1. That would be, r would be 10. Okay, so that's what's happening for us. So it's good if you can list as much stuff as you can. So we know n is equal to 11. We know r equals 5. Now my x, this entire thing here is 2x. That might look a little strange, but that's what's happening. Y, the blue blob, is 3y. We know n, we know r, we know r. Okay, so we need to figure out this guy, but I'll write that out in the formula first. So we're going to fill out this whole formula. And then let's go from there. So we've got 11C5. So that's going to be something we're going to throw into Desmos. And then our x is quite literally 2x over here. And then n minus r, 11 minus 5. And then our y is 3y. And that's raised to the r, which is to the 5th. And then we have to simplify some things. So I already did in Desmos. I took this and evaluated that, and you should go do it too. In fact, pause this video, go do that, see if you can do it correctly. You should get 462. And then this guy simplifies to 2x to the 6th. And then don't forget you're raising the base to the 6th power as well. So you now have 64 x to the 6th is what that simplifies to. And then 3y to the 5th, and 3 to the 5th is 243. And then these all need to be multiplied together. And when you do that, good Lord, you get 7185024 x to the 6th, y to the 5th. And this entire answer went into varsity. Okay? So there were a couple of steps there to figure that out. Some of it was explanational. Like this part, you wouldn't have to rewrite out again. You can just know that R is going to be the number term you want minus 1. X comes, or N comes right out of here. X is this part of your binomial. Y is the second part of your binomial. And then just plug them into the formula that you have. Okay? All right. We have, I jammed a lot of stuff on this page. We are not going to jam a lot of stuff on your page. All right, next problem. If you're asked to write the first X number of terms in a binomial expansion and the N value is very large, then basically you're going to use the same formula to help you. So we're going to do essentially what we just did. We're going to use the binomial theorem. And here is the question. So it says, write the first 3 terms in the expansion of x plus 2 to the 16th power. All right, so I know that I'm going to need, for my first 3 coefficients, well, essentially here, I'll lay this out the same way I laid out the last guy. We'll just use this little formula for each of them. We're going to use NCR x to the n minus r y to the r for each and every term. So what we're going to do, and I kind of like to lay these out like this. So my first 3 coefficients are going to be, I'm going to have 16c to the 0, 16c to the 1, and 16c to the 2. Well, I know that this is going to be 1, this is going to be 16, because we already talked about those, right? If this is 0, this is always 1. If this is 1, this equals n. And then I have to go figure that one out. And that one I've got already done, and that is 120. So those are my coefficients. So this part I already have essentially finished. Then I just have to fill in all the rest. Well, I know that n is going to be 16. And depending on the term that I'm looking for, right, kind of will help me figure out what I need here. So in my first term, remember in your binomial expansion, my very first term, my power on my x is going to match my n. So, because my r is going to be 0 for my first one. So I know I'm going to have, and we could kind of figure these out long term, but remember, let's go back here. Remember how this happened where your very first one had an x but no y and your power matched this? I mean, you can utilize this information. And then down here, you also had a definition. So the first one was x to the n. Well, your n on this one, was it 11, 13? I don't remember. 16? So we know our first one is going to have an x to the 16th power. And then the second term is going to drop 1 power off of x, and your y is going to be 1. Then you're going to drop 2 off the x, and your y is going to be 2. And then drop 3 off the x, and the y is going to be 4. So it's going to keep going up and up and up and up. So we can just apply that. And if you can do your coefficients, you don't have to really mess with this formula a lot. Because what I know is this is going to happen. I'm going to have x to the 16 on the first term, y to the 0, right, which is 1. Then I'm going to have x to the 15, y to the 1, and then x to the 14, y to the 2. And remember that your exponents have to equal 16, right? And then my coefficients. So I have a 1, I have a 16, and I have 120. I have addition signs between all of these, unless your coefficients ended up being negative. And then you just simplify. I don't need this 1, so this is just x to the 16th plus 16x to the 15th plus 120. Oh, I have a y on here. 120 x to the 14th y squared. Now, if I needed another term, it would be x to the 13th y to the 3rd. And then the next one would be x to the 12th y to the 4th, right? It would just keep dropping one off the x, adding one to the y. So, oh, I made a boo-boo. Do you know where it is? I didn't take this 2 into account. I don't actually have a y. What I have is a 2. So, all right, let's put the 2 in where the y is. X to the 16th plus 16x to the 15th times 2. Maybe this is a better way to do it. Just substitute. X to the 14th times 2 squared. So now I got to do a little bit of simplification. So x to the 16th plus 2 times 16 is 32. This is a 4. And 4 times 120 is 480. And then this is the actual answer that needs to go in. So there's lots and lots of places to make little strange problems. All right, next, let's talk about Pascal's triangle. Do I want to? I don't think I do. Yeah, I probably want some lines. Pascal's triangle. Excuse me while I shut a gate for a minute and keep this dog from going out here all the time. It's being very annoying. All right. Pascal's triangle is a triangle of numbers where you're going to start with a 1, and a 1. And then what happens is the next line, it always starts with a 1, and then you add, if there's two numbers that can be added, you add them. So 1 and 1 is 2. So these kind of like go together to make that guy. And then a 1 on the outside. Always a 1. Add these to get a 3. Add these to get a 3. And then a 1. So we get a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Then a 1 on the outside. 1 on the outside. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. 1 on the outside. 1 on the outside. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 5 plus 10, well, 10 plus 5 technically, doesn't matter, is 15. 5 plus 1 is 6. 1 on the outside. We'll keep going. One more row, and then you're going to add a few. 1 on the outside. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7. 1 on the outside. All right, so can you kind of see what's happening here? Like, those are continuing down. Now, here's what's going on. All right, this is considered the 0th row. This guy is the 1th row. I know this sounds a little bit ridiculous, but this is the 2nd row, 3rd row, 4th row, 5th row. You get the idea. 6th row, 7th row. So I did 7. I want you to finish this to the 10th row in your notes. Okay, so you're going to add 3 more rows. You may need to do it on a separate sheet of paper or just start smaller or whatever. Then also highlight when you're done. I only want you to highlight those last 3 rows. So once you're all done, you're going to take your highlighter and highlight those last 3 rows so that when I see your notes, they stand out very nicely. Okay? Now, take a look back at your notes to the very first expansions that we did. I don't know. Here, wait. I'm going to try to do this. This may or may not work. Hold on. Dual page display on. I'm going to pin that page. This page. View. Pin. Okay. Now, okay. So you should be able to see both of these. Take a look. Oh, it's kind of small. And there's so much writing on it. Take a look at the coefficients in the binomials. In this guy. I'm going to try to write on. I'm going to write more on here. In this second row, where n is 2, the coefficients are 1, 2, and 1. We'll take a look over here in the second row. 1, 2, 1. Take a look at the third row when n is 3. 1, 3, 3, 1. 1, 3, 3, 1. Take a look at the next row. 1, 4, 6, 4, 1. Take a look at the fourth row in Pascal's triangle. 1, 4, 6, 4, 1. So Pascal's triangle, these numbers match up with the coefficients in the binomial expansion. So if you don't have some huge, crazy, wild expansion to do, all right, I'm going to get rid of this dual view because I need all the space on the page I can get. So dual page unpin. All right, and then I got to go back to my last page. You can actually utilize this to expand out Pascal's triangle. So let me show you how that's going to work. So you have, if asked to use the binomial formula to expand, you can use Pascal's triangle. So expand x minus 3 to the 5th. Okay, so what you want to do is you want to find the 5th row. So that's this guy. And what I like to do is actually write down those coefficients near the problem I'm doing. So 1, 5, 10, 10, 5, 1. And you'll see why I'm doing that. Okay, so now what I'm going to do is this is my A and this is my B. So here's how I'm going to make this work. I'm going to take, do I want to change colors? I'll try to change color. All right, now this is going to be a little crazy. So coefficient, my first coefficient on the first term is going to be 1. Then I'm going to take my x term to the n. I'll do that in orange. So the x to the 5th. And then the y term, which is -3, to the 0. Right? I take the x to this power, the y to no power. Then I'm going to have a plus sign, and then my next coefficient. So now a 5, and then my x to the 4th. So I'm going to drop a power, and my y to the first. Go to the next coefficient, 10. Go to my x. I'm trying to drop a power. Now you have to be careful. If I had a coefficient on my x, like a 2, I'd want to put my, and maybe I should just to be more careful. I should probably write this like this for you guys. Right? Just that's the better way to do that. And then my y is going to go up a power, -3 squared. And then plus, always a plus. Next coefficient. Oh, orange. My x is going to drop a power. My y is going to go up a power. Next coefficient. Orange. My x is going to drop a power. My y is going to go up a power. Plus my next coefficient. And I would draw all these out. Don't take anything for granted. My x goes down a power. My y goes up a power. Double check that your exponents equal 5 on every term. 5 plus 0 is 5, 4 plus 1 is 5, 2 and 3 is 5, 3 and 2 is 5, 1 and 4 is 5, 5 and 0. Then simplify stuff. Okay, so I'm going to go down. So, and you can cross stuff out, right? 3 to the 0 is 1, so that's going to go away. X to the 0 is 1, so that's going to go away. You have to be careful with your terms too, right? Like this is going to be just x to the 5th. -3 to the first is -3. So -3 times 5 is -15 x to the 4th. Then this guy's a 9. 9 times 10 is 90. 90 x to the 3rd. Then this is a -27 times 10 is -270 x squared. -3 to the 4th is 81. 81. Oh, where is this in there? Oh, that's a different problem. We're going to do another one of these in a minute. 81 times 5 is 405. That's a plus 405 x. And then -3 to the 5th is minus 243. So this whole thing is what you get if you were to multiply x minus 3 out 5 times. But you were able to do it easily by just multiplying and using these things from that expansion, right? So we'll do another one. I'm going to go down the page here a little bit, and I'll kind of try to keep the same idea. Expand. Now this one's a little bit different because it's got a 4x squared plus 3y to the 4th. So we want the 4th row of coefficients. So 1, 4, 6, 4, 1, which is the 4th row of coefficients. 1, 4, 6, 4, 1. And then I'll do the same things. No, now my x value is this 4x squared and my y value is 3y. So we start with our coefficient. So I have a 1. And then my x value is 4x squared, and that's being raised to the 4th. And then my 3y is being raised to the 0. Plus, next coefficient, 4. My x is 4x squared, right? You're taking this whole thing as your x value. And then I'm raising that to the 3rd. You're taking this whole thing as your y value. And I'm raising that this time to the 1st, right? Dropping your x's, raising your y's. plus 6, 4x squared to my second, times 3y also to the second, plus 4x squared to the first, times 3y to the third, plus 1 times 4x squared to the 0, times 3y to the fourth. Check your exponents. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. Now, the ones inside the parentheses, they don't matter. It's the ones on the outsides. 2 times 2 is, or 2 plus 2 is 4. 3 plus 1 and 4 plus 0. Now you've got to be a little bit more careful. So this guy doesn't matter. This doesn't matter. This doesn't matter. This doesn't matter. But you do need to be very careful here because you're now raising 4 to the fourth, right? And x squared to the fourth. So remember, you're multiplying these powers here. So this actually gives you 4 to the fourth is 256. And you multiply these, so you get x to the eighth. And there's no y on here because that one cancels. Now, what I did, I kind of went through here and I multiplied these and said, well, that's a 12y. And then this is going to be a 64x to the sixth. And then I multiplied in the next step. Actually, let me move this guy down a step. So I have 60, or what was that? 256 x to the eighth. And then, so 4 times 3y is the 12y. 4 cubed is 64. X squared cubed is x to the, I have a boo-boo in my notes, x to the sixth. So that's going to give you 768 x to the sixth y. And then here, 9 or 3y squared, this is 9y squared, times 6. 9 times 6 is 54. And then I'm multiplying that by 16x to the fourth. And 54 times 16 is 864 x to the fourth y squared. And then this guy's, let's see, 27y to the third times 4. Well, this would be 16x squared. And then you can multiply that out, and that's going to give you 432 x squared y cubed. That's gone. 3 to the fourth is 81 y to the fourth. Okay, and that whole big old mess is your binomial expansion. So, I mean, can you imagine multiplying, like foiling that twice and then foiling your products? Oh my gosh, it would be a nightmare. So that is, for me, I love that. I mean, you could use the expansion from the combination formula, the binomial expansion, but man, if I can use Pascal's triangle, I just love it. It's just so much simpler. All right, so that's 11.5. Hope you love it. Toodaloo.